Hi, my name is Callie Chappelle, and thanks for tuning into this video about currents in the magnetic field using the Biot Savart law. So, one thing that's really cool is when you have current moving through a wire, it actually creates a magnetic field. That's really interesting, but what's even more interesting is the magnetic field created by a current flowing through a wire is actually perpendicular to the direction of the current flowing through the wire. And when I say perpendicular, it's probably going to raise a little red flag in your mind that things that are perpendicular are often vectors that are perpendicular are often represented by a cross product. So I know if you've been studying E&M, you're probably sick of cross products, but here is another crucial time in which you will be utilizing our friend, the cross product and the right-hand rule. Now, a short disclaimer, this video is going to incorporate the normal right-hand rule and also what I like to call the thumb straight curved rule, which is a slight variant on the normal right-hand rule. You don't have to ever use any variant of the right-hand rule. You can always just use the right-hand rule. But in this case in particular, it's much easier to use a special variant. Now, if you're not familiar with the thumb straight curve rule, well, you should watch the video about the variants of the right-hand rule to make sure you're up to snuff with that, because it gets a little bit confusing. So, we have a magnetic field that is perpendicular to the direction of the current. And we know that it's represented by the cross product. So what is that cross product? Well, the cross product represents the force. So let me make sure that I have my pen in the right direction. So the force due to the magnetic field created by the current in the wire is equal to I, the current flowing through the wire, L, which is the length vector of the wire, which is simply the length of the wire in the direction of the current flowing through it, cross B, which is, as we know, the magnetic field, okay? The magnetic field created by the wire, okay? So conceptually, what's happening is we have this induced magnetic field created radially or emanating radially outward from this wire that has current flowing through it, okay? And the direction in which the induced magnetic field is created is determined by the direction of the current through the wire, which makes sense, right? If you have current flowing one direction, it's going to make the magnetic field go a particular direction. If you have current flowing a different direction, it makes current flow the other direction. So how did we even figure this out? Well, this guy called Oersted, who has a weird spelling of his name that I never would have expected, weird not being a bad thing, must have had a bunch of compasses and also wires with current running through them, and he found that when you have compasses around a wire with current, it instead of lining up with the Earth's magnetic field, instead creates this closed loop. And this is the basis of what we're saying over here, that current flowing through a wire creates closed loop or creates circles around the wire. Now, how do we determine the direction of these closed loops around the wire, these closed loops being the induced magnetic field? Well, we use this thing that I said was called the thumb straight curve rule, in which you orient your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field. Now, if you want to know the magnetic field at a particular point, a crucial piece of information is that the vector representing the magnetic field at that point is always tangent to this circle. Okay, so like let's say the circle is going this way, the magnetic field is going this way. If you wanted to know the magnetic field vector at this point, let's say this is point P, it is perpendicular to the circle that we drew here. Okay, so now that we have a good understanding of the relationship of the magnetic field and the current, then we want to talk about how we can quantify it, because of course physicists love conceptual things, but we also want to know something about how it works and how we can utilize math to better understand these natural processes. And to do so, we use this thing called the Biot Savart law. I know it's not how I have no idea how to pronounce that word. That's how you pronounce it. Okay, and essentially what we're going to do before you freak out is we add up the vector field sum of the magnetic field for each piece of current, what we're going to call a ds, in a particular wire. So I always like to understand things visually first, and then we're going to use the math to fit into that. Okay, so I'm going to draw a wire right here, a really fat wire. Okay, that wire is not very straight, but that's okay. Actually, I'm going to draw it slightly more curvy. Okay, there we go. So here's our wire, and this wire has current flowing through it going in this direction, okay? And there are a couple of things that we need to know. So first, just thinking about this, we are going to look at what happens at point P. So we have some random point here out of space, and we want to know what is the magnetic field look like at this point, as contributed by all the sub little parts that make up this long wire with the current flowing through it. So in order to figure out, I mean, obviously it's too hard to conceptualize all of these simultaneously at once, so we're going to utilize some tricky math to divide these into little tiny pieces that we're going to call ds. And we're going to figure out the contribution that the magnetic force of each ds and how it contributes to kind of the sum total of all the magnetic forces at point P due to this wire. Okay, so we need to look here. So here we were talking about I cross or IL, and this vector, this ds vector, is tangent. Oops, it's not the color that I wanted. Is tangent to the wire. Okay, so this is ds, and this will always be perpendicular to the radius, and that is the length of space between the wire and point P. So that we're going to call R, okay? And I said it's perpendicular, so let's note that it is perpendicular here, okay? And now we want to figure out the direction. Well, actually, no. What I'm going to do now is actually, now that we have this set up, now we have some intuition that we're trying to figure out how much of the magnetic field, what the force of the magnetic field is from all of these points here at point P. Let's look at what the math says. Okay, so I'm going to scroll down really quick, and I'm just going to write out the law, and then we'll break it down. Okay, so the Biot Savart law says that dB, so all the tiny little pieces of the magnetic field that is contributing at this point P, is equal to mu naught, which is the permeability of space, over 4 pi times I times ds, so I remembers the current, ds is all of those tiny little pieces, cross r hat, which is just the unit vector of r, over r squared. Okay, so let's go through and talk about what all of these pieces mean. So this term, the mu naught over 4 pi, this is representing the strength of the magnetic field, and this mu naught, that's just a constant. Okay, now this term, or this section, this is the vector sum. Okay, this is the vector sum. So remember, we're trying to sum up all the vector parts of the magnetic field here at point P. This is the part of the equation that does that. And here, this is the last one down here, this r squared. This just explains how the strength of the magnetic field changes as you get further and further away. Of B field, that's the same thing as saying magnetic field, changes with R. So let's say that P, instead of being here, was out here. Well, as you get further and further away, this is pretty intuitive, from the wire, the magnetic field gets weaker and weaker and weaker, okay? So if R is increasing, then this dB term, or what represents the magnetic field, the integral of that, gets weaker and weaker. So that's just what this says. Now, please keep in mind that at the end of the day, we want to figure out what B is, not dB, or the derivative of the magnetic field. We want to figure out B, so we're going to have to do some integration. And when you integrate this, the strength of the B field is proportional to 1 over R, not 1 over R squared. So that's a little bit notable. Now, we can rewrite this. If we don't want to always be doing the cross product, we can rewrite this as dB equals mu naught over 4 pi, so that's the same thing, times I ds sine theta over r squared. Now, you'll notice that this part is the only part that's different, and all that comes from is the definition of the cross product. So if we have A equals B cross C, Well, this can just be rewritten as A equals B times C times theta, which is the angle between B and C, okay? Oh, I realized that I have an error here, okay? So I'm sorry, I said this is always 90 degrees. No, that's not always 90 degrees. What is always 90 degrees is between L and B and the force due to the magnetic field. This is actually theta, so this can change based on where it is. So for example, if we have a curve here, let's say we have a curve like this, and we have point P out here, well, if we have R here, and we have a ds here, this would be theta. But let's say that we have another point down here, and we have a different ds. Well, this would be theta. Okay? So it's always changing because this is always tangent to the curve. Okay, so our theta is changing. That's why this is not always constant. Okay, cool. So now we know that. Let's talk about what happens when a B field is created. So, oh, actually, one more thing that I want to do. I want to talk really quickly about the permeability of free space. This is mu naught. What's really really interesting about this is actually this is a made up number, and it's actually used to define both amps and coulombs. So it's really interesting that this is kind of an arbitrary number that physicists made up. But what's really cool is 1 over the square root of mu naught epsilon naught. Remember, this is the permeativity of free space, this is permeability of free space. This actually equals 3 times 10 to the 8th meters per second. Now, if this number looks familiar, that's actually the speed of light. So this is super cool. That tickled me when I was in class, and yeah, I'm a nerd, but still. Okay, so last thing that I want to talk about here, really quick, before we delve into 2 examples, the case of using the Biot Savart law to figure out the magnetic field at an infinite line, and also using a curved wire. I just want to reiterate the basics really quick. Okay, so if we have a wire, and the wire is coming out of the board at us, okay, so this is what we know. If we're talking about something in the z or negative z direction, this is in the positive z direction. If it would look like this, it would be the negative z direction going away from us, because this looks like the feathers of an arrow. We know that the field created by a single current element falls off like 1 over r. Okay, so here next to the wire, I'm using the right hand rule to figure out the direction of the magnetic field. So it's going this way. It's really strong, but as we get further and further away, it gets weaker. Wow, that was a really terrible circle. And weaker. Obviously, this should actually be completely symmetrical, but it's not, because I'm bad at drawing on this drawing board. Okay, the next thing that you should know, and this is somewhat tied to the definition of a cross product, is that we have a maximum field when theta equals 90, and we have a minimum field when theta equals 0. So what does this mean? This means that we have a maximum B field when ds and r are perpendicular. Okay, so what would that look like? Well, if we have some axes here, okay, so this is the x direction, this is the y direction, and we have ds going this way, and we have r going this way, so theta, the angle between ds and r, oh, we should label r. When theta equals 90, then of course, remember we set up here that using the Biot Savart law can be rewritten as, right, I ds sine theta. Well, sine theta is the same thing as saying the sine of 90. Well, that equals 1, which means that this term is at its max. And we also have a min. Our minimum magnetic field occurs when ds and r are parallel. So again, we have our axes. Okay, here's the y-axis, here's the x-axis. Let's say that we have r pointing this way, r is pointing that way, and ds is also pointing that way. Well, the angle between them is 0, so theta equals 0, and we know that sine of 0 equals 0. So that is super important to know. And the last thing that I just wanted to reiterate here before we jump on the bandwagon of doing more complicated things is, again, if we have this wire that's pointing out at us and we have this wire is creating a magnetic field around it like this, the direction of the magnetic field at any particular point is always tangent to this circle, okay? So that's like this. Let's see, if it's coming out at us, the direction of the magnetic field generally can be determined by the thumb straight curve rule. So my thumb is going out of the page in the direction of the current, and my fingers are curling around in the direction of the magnetic field. At each of these points, so let's call this point A, the magnetic field is going this way. At point B, the magnetic field is going down. At point C, the magnetic field is moving to the right. And at point D, the magnetic field is going up. Alright, so now let's talk about special cases of the Biot Savart law. So we just talked about what the Biot Savart law is, but it's in terms of dB. So what we really care about, we don't care about the derivative of the magnetic field. We want to know what the actual magnetic field is. So in order to do that, we integrate dB, and that gives us B over the distance that we're interested in. Okay, so we want to sum up the individual contributions of each piece of wire that each piece of wire contributes at point P, so that's why we integrate, okay? So the first example that we are going to do is the example of the infinite. Actually, I don't want to use my horrible handwriting. I just want to type this out. That was a really good idea that I should have thought of a long time ago. Is in the case of the infinite line. So before we, again, do the math, let's draw a quick picture. So again, we have our handy dandy wire. So here's our wire. And again, we're going to be interested in, oops, wow, that's changing colors and that's not what I wanted. Come on, computer, work with me, please. There we go. We want to know the contributions at point P. So I'm going to draw point P out here of many different little DS's, okay? So here is a DS. So actually, I'm going to move DS up a little bit because this is going to make our understanding of determining theta a little bit easier. Alright, so we have DS. And again, we always need to know the radius between point P and DS. So, let's see, I'm going to make a little line here using this straight line creator. Okay, so we have this line, and we're going to call this little r. Okay, that represents the quote-unquote radius between DS and P. But then we also have this line. We have this distance that is, oops, I was trying to make a straight line and I was failing. This distance between P and the wire. Okay, this is a wire again, and this wire has current I flowing through it up this way. It also has this distance, which I'm going to call big R, and that's not changing, okay? What is changing is this little DS, this is zooming whoop, up here, up the wire, and as it zooms up, R is changing. It's getting smaller, smaller, smaller until we get to where big R is, and then it's getting bigger, bigger, bigger as it swoops away. Okay, so let's see if there's anything else that we want to define here. Okay, yes, there is this distance. So this distance between big R and little r, we're going to call this S. And that's just arbitrary. I just made that up. You can call whatever you want. And then we also have a couple of relevant angles. This angle, which I'm just going to arbitrarily call theta, and this angle, which I'm arbitrarily going to call phi. So before we do anything, we want to figure out the direction of the magnetic field, okay? And we figure out the direction of the magnetic field just like we were doing above using the thumb straight curve rule. So my thumb is going to go in the direction of the current, and my fingers are going to wrap around in the direction of the magnetic field, okay? So what I'm going to do now is draw that just so we're all on the same page. So here's my thumb. It's pointing up because that is the direction of the current, and then my fingers are curling around like this. Curling around like this. So what is the direction of the magnetic field here at point P? Well, it is into the board. So I'm gonna just draw it like this. The magnetic field is into the board because my fingers are moving straight back at point P if I was about to wrap them around in the direction of the magnetic field of this wire. So we know the direction. So we use the straight curve rule to figure out the direction of the magnetic field at the particular point. But what we want to know is the magnitude too. Okay, so direction, we're going to use straight curve rule. And then 2, we're going to magnitude, we're going to use the Biot Savart law. And the end game is just going to be an equation that you can use in any case of the infinite line. But what I'm going to do is give you a preview of what the end game is, and the magnetic field at point P for an infinite line is mu naught, which remember is the permeability of free space, times I, which is the current moving through the wire, over 2 pi r, and remember this r is referring to this big R, so that's the distance between the wire and point P. So if you are busy, you can stop this video right now or skip ahead to where I talk about the case of the curved wire. But right now I'm actually going to go through and do some of the proof about where we got this, because I personally really hate just having equations thrown at me. I want to know where they came from. So I'm going to do that real quick. So first we're going to start with what we know. So the Biot Savart law, like we started at the beginning of this video with, is dB mu naught over 4 pi times I times ds cross r hat over r squared. And remember, we can rewrite this as mu naught over 4 pi times I times the magnitude of ds times the magnitude of r hat times sine of theta, and theta is right there. Sine of theta over r squared. And this is just a unit vector, so this just goes to 1. And then, yeah, that's what we're doing first. Alright, so next we want to figure out what is sine of theta. So we know that sine of theta and sine of phi are the same thing. So let me just write that down for posterity. Sine of theta equals sine of phi. And we know that sine from SOHCAHTOA is opposite over hypotenuse. So phi, opposite, is big R, over hypotenuse, little r. So we know that sine of theta equals big R over little r. So let's sub that in right there. And that gives us dB equals mu naught over 4 pi times I times ds times, we're not doing r because it's just 1, times big R over r cubed, right, because here's that other r squared times r is r cubed. Okay, the next thing that we want to do is sub in what r is. So we know from trigonometry that r squared equals s squared plus big R squared, or r equals the square root of s squared plus r squared. So we're going to sub that in here to get this. dB equals mu naught over 4 pi times I ds big R over s squared plus r big R squared to the 3 halves. Where did this come from? Well, it's already the third, and this is the same thing as saying s squared plus r big R squared to the 1 half. So multiplication rule, 3 halves. Okay. And then we are going to integrate this, so integrate both sides. What are all constants? That's a constant, that's a constant, that's a constant, those are constants. So the only thing that we're really integrating is this. And then we have to do, so essentially, let's see, so we integrate this, the s's cancel out because this is going to also become s to the 1 half, and that's all that we really care about. So the end game, this makes a lot of sense. Also, when we do this, we end up getting these r's will cancel out too. So if we integrate this from negative infinity to infinity, we get our final results, b equals mu naught I over 2 pi r. 2 pi big R. Okay, that wasn't too painful, was it? Cool. So the other thing that I wanted to do in this video is do the second case, and that was the case of instead of if this was a straight wire, what would happen if this was a curved wire. So let's write that here. Curved wire. So what does happen? Well, again, let's draw a quick little diagram. And I want the fat brush back so I can do this well. So here's our curve, and again we're interested in what the magnetic field is at some point out here, point P. So let's draw our diagram again. So again, our current is just going to be flowing in the same direction to make this easy for us, and we have some point ds, some ds, and we're going to sum up all these ds's, the sum of all of the magnetic field from all the ds's at point P, to figure out what the total magnetic field is due to this wire at point P. So we have now this ds, which is, if I zoom this up a little bit, is tangent always to the curvature of the wire. And then we have, again, some radiuses that we care about. So there's one right here, and let's just say arbitrarily we have another point right down here. So we're going to actually look at two radiuses, and you'll see why in a second. So we're going to call this one big R, and we're going to call this one big R2, and then the angle between these two big R's, which are the same, we're just going to call phi. So this should be enough for us to do this. So the first thing, again, like we did before, is we're going to figure out the direction of the magnetic field at point P from the thumb straight curve rule. So direction, again, is straight curve rule. So what we do is put our thumb in the direction of the current and stick our hand in the direction of our fingers will curl in the direction of the magnetic field. So if I wanted to draw what I'm doing in this case, my thumb is like this. That's a really great thumb for sure. And my fingers are curling this way. So my hand is kind of like that, okay, where my thumb is going up and my fingers are curling around like this, and that is the direction of the magnetic field. It was kind of a challenging hand orientation to get right. So let's figure out what the magnitude is, because that is where this is a little bit tricky, because the direction's not hard once you get down the right-hand rule, but the magnitude is a little bit trickier. So the end result, again, if you just want to skip to the end, if you're a SparkNotes person, it is mu naught, which is the permeability of free space, times I, times this phi, over 4 pi r. So let's figure out how this works. Let's do the proof really quick. So we know from Biot Savart that dB equals mu naught I times ds cross r hat over 4 pi r squared. Now, what's kind of interesting here is in this case, the magnitude of ds cross r is actually just equal to ds. And the reason why is, again, this is just 1. But the direction at any point, dB is always going to be pointing in the same direction. So no matter where I am on this wire, dB at P is always going to be pointing in. And so if dB points into the board or in, we can add up all of the pieces of dB without worrying about the direction. So we can just take the magnitude because the direction's always the same. So that's why this is legit. So given that information, we can rewrite this as mu naught I ds over 4 pi r squared. And next we're going to think back to the definition of a radian, and that is phi equals s, which is the arc length, which in this case the arc length will always be this tiny little ds because we're summing it up over the course of the length of the wire, over r. Therefore s equals, let's see, phi times r. So we can also sub that in. Oh, well, that's coming in a second, because we need to do our integration first. And what are constants? That's a constant, that's a constant, that's a constant, that's a constant. So when we integrate this, all we're doing is, well, let me just write it out. U naught I over 4 pi r squared times the integral of ds, which when evaluated is just s. So that's b equals mu naught I times s over 4 pi r squared, and s we don't really care about. What we do care about is phi. So then when we sub this in for s, we get mu naught I phi over 4 pi r, because this r is going here and these r's cancel out. So you're just left with one r at the bottom, and that is where we get this definition of the electric field at point P around a curved wire. So I hope this video was helpful for you to understand this a little bit better. The next video is going to be pretty short and just talk about what happens when you have a force between two wires, and also the field due to a current loop and coils. So please tune into that video if you're still confused. Hopefully this is a good base of understanding for the Biot Savart law.